Greetings. Welcome to my lecture on convolution and Laplace transform. So we'll be talking about what convolution is and what is the connection between convolution and Laplace transform, and we'll define the convolution and give you the theorem and use it in solving differential equations. Fundamentally, the word convolution in mathematics, if you just forget about Laplace transform itself, is special products. Just like cross product and dot product, it's just a different product that's defined by, so if you say f convolved with g, mathematically speaking, it's simply just a definition, a special integral that looks like the integral from 0 to t f of, let's say f of u g of t minus u du. It's just a special integral defined, or you could even write this as 0 to t f of t minus u g of u du. It's commutative, so you could f convolved with g, same thing as g convolved with f. So mathematically speaking, convolution is just a definition of a special integral. And just looking at it from only a mathematical point of view and not even looking at it from a Laplace transform concept, would basically be just a definition of an integral, this particular integral. And so from a mathematical point of view, you'll just say, okay, whatever. But what's interesting is, and what happens is that when Laplace transform comes in, when it comes to convolution, and it turns out that if you take the Laplace transform of a convolution, something very interesting and magical happens. Because, you know, if you want to take the Laplace transform with the convolution by definition, then it'd be a horrific integration process. Because there'll be the integral from 0 to infinity of e to the minus st f of t. But f of t is f convolved with g, which is itself an integral of, let's say we go with the first one, f of u g of t minus u du. And then this is dt. So it becomes a double integral every time you want to find the Laplace transform of a convolution. And so far, it's still just a miserable problem. Okay, great, that's horrible, so I hope I never see this kind of thing. Well, what's interesting, and this is where the magic takes place, and that's why when we talk about when you learn Laplace transform, one of the most important thing and most interesting things, or most like natural phenomena that it just exists and it is, and it happens, is the fact that when you take the Laplace transform of a convolution, you get a product of simply the product of those two functions separately in frequency domain. So if you take the Laplace transform, it turns out that way, that if you take the Laplace transform of a convolution, you basically just get f of s times g of s. And that's where the magic takes place. So, and that's why it's so important. So, and why is that important? Well, because first of all, it's nice from a mathematical point of view, just the symmetry here is incredible. Because it's, you know, instead of, if somebody says find the Laplace transform of a convolution, instead of having to do this double integral, I could just find the Laplace transform of the first function, f, and I have to just find the Laplace transform of the second function, g, and just multiply them together, and there's my Laplace transform in frequency domain. And that's why it's in Laplace transform and convolution are like interconnected in concept, because Laplace transform bring a very boring formula in mathematics that's called the convolution, and it brings it to life and makes it very, very applicable to sciences. Now, why is that important to sciences or engineering? Well, you know, it turns out that a lot of times when you look at solutions in frequency domain of differential equations, you always see that the solution is always, like, not always, but sometimes a product of two functions in frequency domain, like, I don't know, 1 over s times s plus 1. I mean, something as simple as that. So you see that most of the time, you see that you could always pull out an f of s and a g of s when you are trying to solve differential equations and you're trying to isolate y of s so you could ultimately find y of t. Now, that's exactly it, because you notice that, well, if that's the case, then most solutions for differential equations in frequency domains are usually product of two functions. And most of the time, not most of the time, all the time, you don't want y of s, you want y of t. But what's y of t? Y of t is the Laplace transform of y of s. But what's y of s? Y of s is, Laplace inverse transform of y of s. And what's y of s? Well, y of s is f of s usually times g of s. Usually it's a product of two functions in frequency domain. And you see there it is. Now what's Laplace inverse of f of s times g of s? If convolution wasn't there, you would think, okay, well that would probably be f of t times g of t, but that's very wrong. It is not. What it is a special integral. It's that, and that has been defined as to be the convolution in mathematics. There's the connection. So that's why convolution very important in the study of Laplace transform. I hope you guys see the idea here. So one more time I'll write it. So Laplace transform of f convolved with g, instead of going through the integral definition, we'll just say that's just the Laplace transform of f of t times the Laplace transform of g of t, which is basically f of s times g of s. And there is the definition of Laplace transform of a convolution. Great. So let's look at it from a very simple differential equation point of view. So let's say I want to introduce you the concept of convolution with looking at a second order differential equation, and I'm going to assume that all initial conditions are zero, so I could get a simple Laplace transform algebraic equation out of it. So let's say my differential equation here is y double prime plus by prime plus cy equals f of t, and f of t is my forcing function. Now, if I take the Laplace transform of this differential equation and assume that all initial conditions are zero, I get s squared plus bs plus c times y of s equals f of s. So Laplace transform has completely converted the differential equation into an algebraic equation. Okay, well, great, we know that. So, and if I solve for y of s, I get that. But let's call that g of s. So y of s is equal to g of s times f of s. Now, g of x, in speaking in the language of electrical engineering, usually g of s is known as a transfer function. Input response, usually a transfer function, and f of s is the input, and y of s is the output. So these are interesting names given to this. And that's just in the language of engineering. And f of s is the forcing function. So that's what you know when you push something, when you turn on a system, that's an input that's been given. So that's a forcing function, and that's the Laplace transform of the forcing function. All right. So y of s is equal to g of s times f of s. All right, so also the transfer function is known as impulse response. Actually, I should give you that name too, impulse response, because it's the response of the system to the impulse given. So that's just the language there. Now suppose that my transfer function here happens to be a product of two functions, as you can see here. So now I want to find the actual solution. So y of t is what I'm looking for, is a Laplace inverse of y of s. And again, Laplace inverse of y of s is g of s times f of s. And there we see the need for convolution. So y of t, which is what I'm looking for in time domain, is basically g convolved with f. And this new operation that answers that differential equation is what we know as convolution. And there is why you see the convolution. I mean, I did it for a general second order non-homogeneous differential equation, and just naturally, it doesn't matter what the functions are, you see a convolution coming out. So I need to figure out an example here so we could actually see what's happening. So let's look at a simple first order differential equation, something so we could all see very simply, and because that the mathematics of differential equation here doesn't matter. I just want you to see the existence of convolution and how it just shows itself in solutions of differential equations. Now, let's see. Let's look at a first order differential equation, dy dt minus ay equals e to the ct. Now you may be able to solve this much easier using the methods you've learned before, but that's not the point. We're trying to see the connection of convolution to the solutions of these equations. And by the way, also there's a lot of these problems that if you give you f of g, f of s, or g of s, and you could just do partial fraction decomposition to solve those kinds of Laplace inverses. But convolution is another option. But there are problems that could be done the other way around, so it's not a bidirectional relationship. So ergo, I'm just trying to constantly trying to convince you of the importance of convolution and its connection to solutions of differential equations and Laplace transform. So let's look at this differential equation. And let's take the Laplace transform of this differential equation. So you get sy of s minus ay equals the Laplace transform of e to the ct, which is 1 over s minus c. So if I, by the way, sorry, that should be a y of s. So if I factor out a y of s, I get s minus a, s minus c, and therefore y of s is equal to 1 over s minus a times 1 over s minus c. So you see, well, actually here you would say, okay, well, if I want to find y of t, I'm going to find the Laplace inverse of 1 over s minus a, 1 over s minus c. And here I'll just do a partial fraction decomposition like you've done before. Well, yeah, you could do that, but we want to use convolution to solve this. So we're going to look at 1 over s minus a as my g of s, and I'm going to look at 1 over s minus c as my f of s. Now, we all know that 1 over s minus a is the Laplace transform of e to the at, right? And we know that f of s, which is 1 over s minus c, its Laplace inverse is e to the ct. That's right. So we know what the Laplace transform of each one of those are. Laplace inverse transform of each one of those are. So therefore, we could just simply here use a convolution definition, because that is a convolution. Laplace inverse of the product of two functions in frequency domain is the convolution of those two functions in time domain. And the convolution of those two functions in time domain will be the integral from 0 to t of e to the a t minus u, right? E to the ct, sorry, cu, it's my new variable, e to the cu du. So that becomes my solution. Now, at this point you'd say, well, it would have been easier for me to just do partial fraction decomposition. Well, in this case, yes, but then there's a lot of cases that it wouldn't be. So, but I just wanted to show you how it's done with the concept of a convolution. Now, we could simply integrate that. I'm not going to go through the integration process of a simple exponential connection there. So I'm just going to write the answer for you. The answer is e to the ct minus e to the at divided by c minus a. So that becomes my solution. There you go. So I can get rid of that 0 there, put it there. So that becomes my solution, and I could have gotten that had I done partial fraction decomposition, but I just wanted to see that. have you guys see that. All right, great. So let's do another example with convolution to see, so that we could start practicing and seeing how it just comes out. Let's give you another example with the convolution. So let's see. We can look at this one. Let's try to find the Laplace inverse of say 1 over s squared plus k squared and see how the convolution will get involved here. So what's the Laplace inverse of 1 over s squared plus k squared to the power of 2? Well, let's look at here as f of s here. See, I'm trying to look at this as Laplace inverse of f of s times g of s, so I can invoke the convolution dragon. So f of s is equal to g of s in this case because of symmetry, and that's equal to 1 over s squared plus k squared. Okay, so now what is the Laplace inverse transform of 1 over s squared plus k squared? Because now I need to know what f of t is and I need to know what g of t is, so I can then convolve them. So the Laplace inverse transform of 1 over s squared plus k squared is 1 over k sine of kt. So Laplace inverse of f of s, which is equal to the Laplace inverse of g of s, is equal to 1 over k sine of kt. So that's my Laplace inverse transform of each one of those. So by the convolution theorem, the Laplace inverse of f of s times g of s, and here I'll just f of s times g of s, which is 1 over s squared plus k squared squared. So the Laplace inverse of that would simply be the integral of 1 over k squared, because there's two of them, the integral from 0 to t sine of ku sine of kt minus u du. So I gave the shift to the second function here. And so they're both sine, right? So you have 2 1 over k, so it gets 1 over k squared. One of them becomes ku, the other one becomes k times t minus u with the shift, du. Now, you could use integration by parts here, but that would be a nightmare. So it's easier to remember that there was a product, there was an identity in trigonometry that you could write the product of two sines as a sum of them, and finding the integral of a sum, it's much always easier than finding the integral of a product. So it was the kind of a product to sum formula, and if you recall, it was sine of a times sine of b. It's 1/2 parentheses cosine of a minus b minus cosine of a plus b. So this is from trigonometry. So I could write sine of ku sine of k times t minus u as a sum, as a difference. So that's called the product to sum trigonometric identity. And with the substitution, I can simply see that the Laplace inverse of, I'm just going to write the expression, s squared plus k squared squared is equal to 1 over 2k squared integral from 0 to t of cosine of k 2u minus t, and the other one will be minus cosine of, and things will cancel out here, so you'll just get kt and du, and that's what you end up with. And if you take the integral, and that's a simple integration process, you'll see 1 over 2k squared. I can pull that out. It will be k here. It'll be sine of kt minus kt cosine of kt. And that'll be and you can write them more combined, but that'll be my Laplace inverse. So really doesn't make it any easier, but then again, there's a lot of scenarios where without the convolution relationship, it wouldn't have worked out. So it becomes a very integral part of Laplace transform, and convolutions are really a big part of that. So let's try to do another example here. So let's say I want to find the Laplace inverse of, let's do another one here, Laplace inverse of s over s squared plus 1 squared. And that's just the Laplace inverse of, let's look at it as 1 over s squared plus 1 times s over s squared plus 1. So it's a Laplace inverse of, again, a product of two functions, f of s times g of s, which then will be the Laplace inverse of 1 over s squared plus 1, which is f of t convolved with the Laplace inverse of s over s squared plus 1, which is g of t. So this is basically f of t convolved with g of t. Now what's Laplace inverse of 1 over s squared plus 1? That's just sine of t. And Laplace inverse of s over s squared plus 1 is cosine of t. And now I'm being asked to find the convolution of sine of t and cosine of t. And by definition, that's 0 to t sine of t minus u cosine of u du. Now again, same thing as before, you could do the product to some identities. Here you have a sine and a cosine. So we have, you could use sine of A, cosine of B. Yeah, these identities are used a lot in this topic. Is equal to 1/2 sine of A minus B plus sine of A plus B. And using that, I can transform the integral, and I'm going to skip the formalities here because I don't need to take the video time for a simple basic integration here. So your integral ends up being 1/2 from 0 to t, and I'm just going to write it out for you. It becomes sine of t minus 2u plus sine of t du. And if I integrate that, I end up with ultimately 1/2 t sine of t. And that becomes my Laplace inverse of this expression. So that's another example of a of the use of a convolution in a Laplace inverse transform. Thank you.